Hello guys, so today I'm going to take you through a short tutorial on how to design a two-way spanning slab using Tekla version 2020. So to begin, when you open your Tekla, this is where it normally opens. This is the window which pops up. So we shall just come to new and come to new document. So once we are at new document, I'm coming to all. You can either come to all or I come to floors over here and select RC slab design using BS 8110. So I'm going to be using British standards for this example. For this demonstration, I'm going to use BS 8110. So we shall click on it. Once it shows this, we'll just come here and click calculate over here. So these are just short notes telling you the assumptions and limitations they're using and the code of design that they're using. So I shall click on calculate. So this is what it shows. So once you click on that, this is what it will show, but I shall just abort and discard. So I want to increase this window. So I'm repeating the same procedure. The calculate which we clicked on. Once you have already clicked on calculate, I just wanted to increase this one. So once you click on calculate, this is the window which will pop up, and it wants you to specify a few things. So before we get to there, this is the slab that you're going to design, the panel. So a slab is always divided into panels depending on your beam arrangement. So the beam arrangement is going to split the whole slab into what we call panels. So these middles, it is panels, and also others are called base. So this middle slab over here is what you're going to use for this design example. And in this design, in this slab, what you're going to, as we can see, the dimensions is 3.85 meters and 3.95. Obviously, the 3.95 is the longest. So normally in design, it's if you're sure with the critical panel, you can depend on it and calculate all the loads, and it will give you the reinforcement which you can use to reinforce the entire slab. It's always advised to, it's a common practice to use the same sizes of bar, mainly for, let's say, the main reinforcement with the same spacing. You cannot have different spacings in the slab, let's say, for the specific type of reinforcement. For example, the main reinforcement for the bottom bars should have the same spacing, and even the top reinforcement bars too should have the same spacing the distribution bars should have the same spacing same applies to the top reinforcement bars. So this is the slab that I'm going to consider. Its dimensions are 3.95 and 3.85. So we come here back to this Tekla software, and the first thing is asking us is slab spanning. So they want us to say whether it's two-way, simply supported, or restrained. So when you come here, you can see that we have 3.85 or 3.95. To know whether it's two-way or one-way is, first you have to calculate the aspect ratio. The aspect ratio is always Ly, which is the longest side, divided by Lx. So if we just punch our calculator over here, punch our calculator, you will find that 3.95 divided by 3.85, so I'm using meters, it's going to give you 1. So a two-way spanning slab is the aspect ratio is less than 2. That is the longest side divided by the shortest side. While the one-way spanning slab, the longest side divided by the shortest side is either greater or equal to 2. So that's what guides on determining whether it's one-way or two-way. So whether it's one or two-way also affects how the slabs, the loads are going to be distributed when you draw the yield lines for the slabs. So I shall not get into that right now. So yeah, those two are what guides whether you know a slab is two-way or one-way. So you just keep that in mind. So coming here, they want us to choose the slab spanning. So we have already determined it's two-way because the longest side divided by the shortest side is less than 2, which gave us 1. So they want us to determine whether it's two-way simply supported or two-way restrained. So coming here, this slab is an interior panel. That's what they always call it. The slab which is continuous on all sides. Continuous in the sense that all this side is no open space. It's connected to other slabs on all the sides in all these 4 corners, 4 sides. So when you come here, we select two-way restraint. For simply supported, it's not connected to slabs or to other slabs on either side, so it's just standalone. There's no connection with other slabs, other panels. So for type of tension steel, we shall use bars. For shear and punching shear, we shall not be using this, because for small panels of slab that are spanning for short distances and of very minimal depth, like the ones which we are using, they have very minimal shear. So we shall not go into determining whether we are putting shear, determining the shear forces and reinforcing for the same. So span deflection ratio check, yes, that we shall use. So deflection in slabs is a very, very important thing to check, because slabs are mainly affected by deflection moments as opposed to beams which are affected by both, mainly deflection and shear. But in slabs, the major force which you always include is the deflection. You must check for that. And reinforcement cover check, we shall check. Include appropriate sketch with calculation output. So this will affect your report, which is going to appear over here. So we shall go next. So this one, click on it, or you can as well as leave it to be if you don't want the sketches. So now we get to this other. Once you click next, this is what you go to, and they want you to input the slab data. So for the depth of slab, for me, I always do some kind of trial and error, but I stick to certain depths of slab. For example, I only stick to 150 millimeters and 200 millimeters. Then I can go to 225 millimeters and going upwards. The reason as to why I stick to these depths is because these depths are very common in construction. And the reason as to why is because 1 inch is equals to 25 millimeters. So while you're choosing the overall depth of your slab, you must ensure that the overall depth of the slab is divisible by 25, because it's divisible by 1 inch, which is 25, because mostly on site and in construction projects, they use inches. Where I am, they use inches in construction. So that's why I must stick to depths which can be easily divided and converted into inches. So 150, also you can also find the wood which they use for for the shutters which they use for the slab casting, you'll find that they are in those specification. You'll find 6x2, the timber is 6x2, you'll find 8x2. So it's easier for them 12x2. So you'll find it's easier for them to easily navigate with depths which are easily converted into inches. So for me, I shall begin with 150. 150. So the cover to outer tension, still resisting sagging, and then there's the cover to outer tension, still resisting hogging. So for those ones who are new to this, when let me just demonstrate what is hogging and sagging. So for example, this is a beam cross section of a slab section over here. So these are the supports. So under loading conditions, this is how the slab is going to deform under loading conditions. In the event that it's not reinforced or poorly reinforced, this is how it's going to be. So this is what they call hogging. Hogging occurs at the supports, while sagging occurs at the mid span of the beam. So hogging at the supports and sagging at the mid span. So this is what we are reinforcing against. We don't want this to happen. So if you look at a slab, if this is the, so there is always bottom reinforcement over here. So for example, if this is where so let me extend this. So I shall rub this on here. So if this is where the reinforcement, this is the section of the beam, the reinforcement which is always put here, this is the reinforcement for hogging because it's resisting these forces and deflection over here. And then this one is the mid span, is what is resisting sagging over here. So that's what they mean by hogging. This one is hogging, this one is sagging. So that's what they're talking about when they talk about hogging and sagging. So for this, I shall put 25. I'm using an inch for the cover. And then assume diameter of steel resisting sagging. I'm going to begin with 10. But you can begin with any bar size. You can always use any bar size you want. But beginning with D8, going upwards up to D12. So partial factor of safety for strength of steel, yes, let it remain to 1.15. And characteristic strength of reinforcement, let it remain at 500. Yeah. Characteristic strength of concrete, we shall use 25, not 35. So for me, this is the slab that I'm going to go with. So yeah, so we shall move to the next portion. So here we are going now just to allow you to calculate the various loads. We're going to put some data to enable it to do the analysis. So the shorter side, it was 3,850 millimeters. The longest side, it was 3,950 millimeters. So design ultimate load per unit area. So for my slab here, how to get that is just to use you must first know your dead or live loads. Live loads will depend on the use of this slab. For example, if it's for residential purposes, there's a code of British standards which deals with that. I think is 639069 or 99. It's 6369. Yeah, I guess it's So I guess it's BS 6369. So that's the one which deals with loads. So that's the code which deals with loads. So for my slab, I'm going to use a live load of 1.5 since this is a residential building. So let me calculate. And then for the dead load, if I add the floor finishes, the screed and the tiles and everything that's going to be here, that's going to be the partitions, that is going to be a dead load. I'm going to I'm going to end up with 5.4 plus the self weight of the slab. So there are factors which you're supposed to multiply with these loads. So I start with 1.4, which multiplies with the dead load, factor for the dead load plus times 5.4. Then I shall add 1.6 times 1.5. So this is going to give us 9.96. Yes, so we shall use 9.96 as our ultimate load per unit area. So shall come here and use 9.996. And then edge conditions. Edge conditions are guided by whether the slab is connecting to other slabs or it has free edges. For example, our case, as you can see, is an interior panel. All the edges are, so this is an edge, all the edges are connected to other slabs, so we shall just take it to be continuous on all edges. So like the way it is here, all the edges are going to be continuous. In the event if we were using this slab, you can see the shorter side is discontinuous, and one long side discontinuous. So with that, you can come and change these shorter edges to be discontinuous. You can change this discontinuous, and even the longer side, one of them, you can change it to be discontinuous. But that's not the case for us. It's an interior panel, and all the edges are continuous. So moment distribution factors on the short and the long side, these ones will remain 1 because I'm not going to redistribute any loads. So, and the minimum percentage of reinforcement, that one you can check with the codes which you are using. For BS 8110, it's always 0.13%. Yeah, for slabs. And other members, structural members in the frame have different minimum percentage of reinforcement and even the maximum percentage. So we go to next. So it has already calculated the area of tensile steel to resist sagging for assumed diameter of 10 millimeters. They have already found this is the area. So we used 10 as the assumed diameter. So since this is the area and this is the spacing, so I'll still stick to use 10 D10 at a spacing of 200. As you can see, it wanted an area of 74, but we're giving it 393, meaning it's sufficient. So select, and then area of tension steel required to resist sagging. So since this one is higher than the first one, meaning this one is for the main reinforcement. So the main reinforcement is the one which carries the most, will require the most area. So we select it. Area of steel required to resist hogging. Area of outer tension steel required to resist hogging. So outer tension steel is outer tension steel is the distribution bar. So also this one we shall just keep it at 10 and choose. So this is where you choose areas and you choose spacing of bars, and it will give you the areas you select. And then this one, the inner tension steel resisting hogging, this is the main reinforcement. You can tell whether it's the main reinforcement or not, checking by the areas. The one which has the most areas is the main reinforcement. So basic span over the effective weight ratio. This from, if you check at the British standards, this one is for simply supported. So we shall go with 26. Minimum, I'm going to be 25, which is an inch. Diameter of links. So these ones are for resisting shear, and we don't really have shear, so there's no need for us to include the links here. And also, you see, in shear forces mainly are always significance when you're dealing with slabs of very high depth. Those ones which are very huge depths are the ones which experience shear. But for ours, the main thing is just deflection. So we shall go to next after choosing those ones. Now it has already finished calculation. We already have our results. It has already checked the bars. As you can see, it's sufficient. Everything area is sufficient to resist sagging. Sagging is sufficient. You can see here, hogging is sufficient. So once you get these results, now you can come to your structural drawings and show them here. So as you can see, so now we are interpreting the data. This is the outer tension steel, outer layer of steel, and this is what they call the distribution bus. And as you can see, they're saying provide D10, provide 10 dia bars at 200 centers. And they're saying outer compression steel is not needed to resist sagging, because here it's tension which is taking place, because this is the mid span. So where sagging is, it's tension which is there, not compression. And same to hogging. Where hogging is, it's just resisting tension, not sagging. It's resisting tension, not compression. So this is the distribution bars, which is called B1, and then the inner layer of steel. The inner layer of steel, this is what they always call the B2, which is the main reinforcement bar. So this is the main reinforcement bar. So even when you come to hogging, this the inner layer of steel, which is here for hogging. For hogging, we start with the outer layer. The outer layer of steel, which is here, this one is the distribution bars. And then the main bar, the main T1, normally they denote it as T1. The main reinforcement bar is this one over here, which is, they're saying we can use D10 to do the reinforcement. So they're checking here the minimum percentage of reinforcement. So there is always the minimum and the maximum, which is 4% of the total area of the concrete. So total area of concrete, you just multiply the height times the length. So that's how you do it. And concrete slab deflection check, there's a way there's a procedure of doing this deflection check. As you can see, it has applied here formula. You have to get the service stress and other things. So I shall not go into that, but this is the process which it goes through. And you can see here the span to depth ratio check is satisfied, so it means it's okay. So that's how you do it. And here is checking the nominal cover for sagging. So this is how you come about it. And here is checking for the nominal cover for hogging. So there are so many things which affect the cover depending on the weather conditions which you are subjecting the structural member. Is it in water? Is it in salty? Is it going to be in a place where they're in an environment which is going to affect the reinforcement? So that way you'll have to increase the cover. So there are other things like fire resistance of the building, and the environment, and other things that you're going to subject the structural member. So that's what guides the cover which you're going to choose. But for me, I'll just go with 25 because most slabs are concealed inside the building and they're not really exposed to a lot of weather conditions and other things that may affect the well-being of the steel. So this is how you design a two-way spanning slab in Tekla tents. Thank you for watching. If you have any questions, please let me know.